So let's take a moment to put together everything we have learned over the last two modules and discuss some guidelines for performance tuning our SQL statements.
One of the critical factors in performance tuning is to understand context. If you are writing something like a web application used in a customer service portal or a line of business application used internally by representatives in your call center, queries to your database must be lightning quick, a few hundred milliseconds at most. First, because these users demand screens that will return within a couple of seconds, and second, because you are supporting a high volume of users, so no one SQL statement can run too long, or else you'll have a bottleneck in your system. Conversely, if you are working on a batch application that runs in overnight hours, the parameters are different. Let's say you're working on an application that generates billing statements for customer accounts. You will probably have a query that will find all of the customer accounts that come due and need to have statements generated for today's date. And this one query may return 10,000 or more results by itself. You still want to tune this query to be as fast as possible, but depending upon the structure of your database and join conditions, this query may very well take 30 seconds or a minute to run, and this may constitute good performance based on the data being returned. And business intelligence systems are yet a completely different use case. Performance is important in all of these cases, but the context is very different in each one. For that reason, you can't make universal statements like, every statement should return within 500 milliseconds, or every query should perform less than 1,000 logical reads. While these rules might work in the first use case on this slide, they are unrealistic in the second two. So what are we to do? So to answer this question, let's ask a different question. When you look at a database schema, how do you identify the key tables in that schema, as it is usually these key tables that will drive the performance of your SQL statements? The first item I consider is what role the table is playing in the database schema. Often you're going to have a number of lookup type tables that contain a few hundred rows or less. These are usually never an issue. When I look at a schema for the first time, I try to identify the tables that contain the data that the application is collecting. These are the tables that contain customer information, orders, billing data, and the like. The data in these tables isn't static. New data is being added to these tables all the time. These tables are almost always significantly larger than the other tables in the database schema. And if you're going to run into performance issues, it's usually going to be on these tables. The second item I try to understand is how do these key tables relate to each other? This is both in a database sense, in terms of understanding foreign keys between the tables, but also in a business sense. How does the business data in these key tables relate? And how does that drive how the user of our application wants to see the data? Most useful business functions will require data from two or more of these key tables. Somewhere within your application, you are probably joining two of these key tables together or performing a subquery against one of the tables from the other or something similar. And it is in these areas, when you have to combine data from two or more of these key tables, that performance problems often crop up first, because of the amount of data involved, but second, because the functions we are performing are more complex than just a simple read from a single table. So you want to identify these key intersections amongst your tables.
Another method you can use to identify high-cost statements is to look for statements that are outliers when compared to other statements in your application. If you have a line of business application with an OLTP database as a backend, and most of your SQL statements have a cost in the teens, but one statement has a cost of 50, the statement with a cost of 50 is the outlier, and this is where you want to look. From here, you want to identify the highest cost operations within the plan. Determine what those operations are trying to do, and then see if you can tune those operations. As we have seen in this module, tuning the worst performing operation in a SQL statement can oftentimes lead to a dramatic reduction in the cost of that statement, and ultimately, the time it takes to process that statement. What are the operations that are candidates to have a high cost? Anytime Oracle has to do a full scan operation, whether against a table or an index, you should be suspicious. You also want to look for operations that have a high number of logical IOs occurring, or operations that return a large number of rows, especially if on a subsequent step many of these rows end up getting filtered out or otherwise thrown away. What can you do in these situations? Often this is a sign of poor indexing, which is the topic of the next two modules in this course. You may need to add a new index that this statement can use, or it might be appropriate to modify an existing index so that it can be more selective. Another option is to consider if it is possible to have a more restrictive where clause to your SQL statement. The more information you give Oracle, the more efficient Oracle can be at trimming down the number of rows it needs to look at and finding the relevant data faster. For example, let's say I have a customers table with 1,000,000 rows in it, and I need to search for a customer with the last name of Johnson. If the data follows the distribution of last names in the United States, then I would expect to get back about 8,100 results. So if I assume I am using an index, Oracle will need to read the data blocks that contain those 8,100 results from the table. And even though we are initially using an index, Oracle still has to do quite a bit of work to read the table data. If, however, I'm able to provide some more information, like the person I'm looking for lives in Colorado and their first name starts with G, Oracle can use this information to be more selective about the rows it queries from the index. And now I might only get back 25 or 50 results from my index operation. This is more efficient for Oracle, but it will also be more efficient for your user, as they're being presented with 50 or fewer results to look through, not thousands. What is important is to think about what your SQL statement is trying to accomplish. There is some business function in your application that your SQL statement is designed to support. So ask yourself what the purpose of this business function is. What data does it need? What data is provided to this function as input? By understanding what function your application is trying to accomplish, you have a better chance at writing a concise, efficient SQL statement that supports that function, but doesn't waste a lot of effort on items that aren't needed in your application. Just like application code, where we want to keep methods short and to the point, we want to do the same thing with our SQL statements. The single responsibility principle applies here as well. Complex SQL statements are hard to test and debug, and they often do a lot of unnecessary work. Plus, every table you join in or other function that you have in your SQL statement to perform is another chance for something to go wrong, like missing an index. So keep your SQL statements short and to the point, and you'll have an easier time ensuring good performance.
As a final thought, don't underestimate the ability of a single costly SQL statement to negatively impact performance across your entire application. What your user feels is a business function that is too slow to be usable. What you see is a SQL statement that takes a long time to run, maybe 20 or 30 seconds when it should only take 500 milliseconds. But there is a darker side to the story. A poorly performing SQL statement is often a very costly statement to execute in terms of resources. If you have a few users in the application function that runs this poorly performing SQL statement, these few instances of the poorly performing SQL statement may be enough to use up all the CPU on the database server or cause enough disk I/O to slow down other statements. This is no different than the situation on your PC, where you have one application using 100% of your CPU or performing a large amount of disk access. Not only is that application unresponsive, but any other applications you are running at the same time also become slow and unresponsive. This same situation can occur in Oracle if you have a few inefficient SQL statements using a disproportionately high amount of system resources. So now that you have the tools, you can understand what your SQL statements are doing and how you can tune them in order to maintain optimal performance. Well-tuned SQL statements save resources in your database, and this can make your application more scalable. But most importantly, they provide an application experience for your users that is more responsive and ultimately more usable.